Hello everyone, welcome to our differential equation class. In this video we introduce simple eigenfunction problems. We are going to start with a brief review of the 2-point boundary value problems we studied in the previous video. Then we are going to introduce the eigenfunctions problem we are interested in, and then we are going to solve a few examples. There are 4 main examples that we want to study. We are going to solve 2 of these examples in this video, and the other 2 are going to be left as exercise. So that's the plan for today. Let's start reviewing 2-point boundary value problems. Recall, in a previous video we said that given a second-order linear differential operator like this one, then a 2-point boundary value problem is to find a function y of x that is solution of this differential equation plus these boundary conditions. Here. So the differential equation contains the differential operator and a given function, a given source function, and the boundary conditions are 2 equations. The first equation contains the values of the function and the derivative evaluated at a particular point x1, while the second condition contains the values of a function and the derivative evaluated at the second point x2, and x1 and x2 are different. And here all these are given constants. So that was a boundary value problem, and in these videos we are interested in 4 particular cases for the boundary conditions. And the first case is called the Dirichlet boundary condition, when we have only the function evaluated at 2 different points in the boundary conditions. That is, these 2 constants b1 and b1 tilde and b2 tilde are 0. So that is this particular case. Then we are interested also on the Neumann boundary condition, which contains only the derivative in the 2 equations, so these 2 coefficients here are 0. And then we have the mixed boundary conditions, which are 2 of them. In the first one, the first equation contains the function and the second the derivative, and here is the opposite. The first equation contains the derivative, the second the function, which are again particular cases of these boundary conditions. So this is what we said is a boundary value problem, and for these boundary conditions and for a particular type of operator, the particular type we are interested in is the operator that has this coefficient equals 0, and this coefficient is a constant, let's call it k. For this operator and this boundary condition, we have proven a result from a previous video, which is the following. Consider a boundary value problem for the function y of x, that is to find the solutions of this differential equation. So the right hand side is 0, and the operator contains only this term, the term k times y, and the second derivative. And then the boundary conditions are any of the following 4 boundary conditions we introduced before: Dirichlet, Neumann, mixed 1 or mixed 2. To write down the theorem, we need r plus and r minus, which are the roots of this polynomial, which is the characteristic polynomial of this equation. As soon as you put an exponential rx into the equation, you get the characteristic equation, which is r squared plus k equals 0. So the root of this polynomial, let's say they are r plus and r minus, are very important to find the solutions of that differential equation, as we very well know. And then we have 2 main cases here. Recall k, this constant k that we have here is non-zero, so it can be either positive or negative. If it's negative, then what is going to happen is that the boundary value problem has a unique solution for each values we choose for d1, d2, and l. Unique solution. This we have proven that this result in a previous video. And when k is positive, then, well, you can see the roots are going to be complex. Here the roots were real, here they are complex. And in this case, we have different results for the solution depending on what are the values of the constant d1, d2, and d3. d1, d2, and L. There is no d3. So we have three possible cases. Either we have a unique solution for some choice of this constant, or we have no solution at all for a different choice of these three constants, or we have infinitely many solutions for a choice of these three constants. So could be either of these three cases, but only for k positive. For k negative, there is always a unique solution. That was the main result in the previous video, and we are interested in this result in our video now because we are going to introduce what we call eigenfunction problems, and these are going to be boundary value problems that have infinitely many solutions. Let's introduce eigenfunction problems, and later on we are going to see how we can use this boundary value problem theorem to find solutions of eigenfunction problems. Okay, what is an eigenfunction problem? To understand a little bit better what is an eigenfunction problem, let's recall what was an eigenvector problem. An eigenvector problem is given a square matrix A. We usually work with 2 by 2, but any square matrix A. Find a number lambda and a non-zero vector V. Solutions of this equation, and the equation says that the action of the matrix on a vector is proportional to the same vector. That was an eigenvector problem, and now we want to introduce something similar where we are going to replace the action of a matrix on a vector by the action of a linear operator on a function, subject to some boundary conditions that they are going to be either Dirichlet, Neumann, or mixed. So what is then an eigenfunction problem? Okay, let's consider a linear differential operator, second order linear differential operator like this one. Then an eigenfunction problem is going to be to find a number lambda and a non-zero function y of x, solutions of a boundary value problem that contains the differential equation, the operator acting on a function is equal to be proportional to the same function, subject to homogeneous boundary conditions, which are boundary conditions like in the previous theorem, but they are homogeneous because the right hand side is 0. So the coefficients d1 and d2 that we mentioned before are now 0. So this is an eigenfunction problem. You see the equation we are solving looks pretty much similar to the eigenvector equation where we are replacing the matrix by the linear operator, as we said before. But now we need to solve a boundary value problem with these boundary conditions. A few remarks about this problem. First of all, we have homogeneous boundary conditions. So the function y equals 0 is always a solution. You see, if you put 0 here, is solution of the differential equation. If you put 0 for the function, everything is 0, and because we have homogeneous condition, they are going to be satisfied. So 0 is always a solution. This is similar to the eigenvector problem where the vector 0 was always solution of the equation, and we were not interested in that solution. That's why we say we are looking for non-zero solutions. Well, here is the same case. 0 is always a solution of the eigenfunction problem, but we have mentioned that the eigenfunctions that we are looking for are non-zero functions. So in order to have eigenfunctions, the boundary value problem we are working with must have infinitely many solutions, because boundary value problems have either unique solution, infinity many solutions, or no solution at all. Here we have a boundary value problem that always has the solution 0. If we want more solutions, that means the boundary value problem must have infinity many solutions. Okay, so essentially what we are doing is we are looking for a number lambda so that this differential equation with the boundary condition either Dirichlet, Neumann or both mixed has infinity many solutions. Okay, that is the condition we are going to use to find lambda. Now, the equation is the eigenfunction equation is very complicated for general operators L like we defined above. Here in this video we are going to focus on the simplest possible operator, which is essentially the second derivative of y. Why do we focus on that operator only? So essentially what we are saying is we are making this coefficient 0 and this coefficient 0, and this coefficient is -1. Could be +1, but we are choosing -1. So that is not there, and this is constant. So why that? Because this is the operator that will appear when we solve the heat equation, and all the work we are doing in these videos is preparation to solve the heat equation. So that's what we want to do. In this case, in the case where we have this operator, the eigenfunction equation looks like this. But we are going to rewrite it a little bit in this form, in the form y double prime plus lambda y equals 0. Again, with boundary condition that they are going to be either Dirichlet, Neumann, or mixed. But this is how we are going to write the equation. Now, to solve this equation, what do? Well, we put exponentials into the equation, and what we obtain the characteristic equation for the exponent. Okay, so the theorem now is where the previous theorem on boundary value problems is used, because the previous theorem says that the characteristic equation must have complex roots for the boundary value problem to have infinity many solutions, because we are solving this equation, and this equation is the equation that we had in this theorem. This theorem says that only in this case we are going to have infinity many solutions. So, and the k in our eigenfunction problem is the eigenvalue lambda. So the theorem above says that this characteristic polynomial must have complex roots, and that means that lambda has to be positive in order to have eigenfunctions. So when lambda is positive, what is happening here? So you see, if lambda is positive, let's double check what we just said. If lambda is positive, then r squared is equal negative lambda. We put it on the other side. That means when we compute the square root, we have plus or minus the square root of lambda, and because there is a negative sign, then we have an I. And that means that the general solution, so you see the roots are going to be complex, and the general solution of the differential equation is going to be something of the form a constant times the cosine of square root of lambda x plus another constant sine of square root of lambda x. And now the only thing that is left is to in order to solve the eigenfunction problem for this operator is to impose the boundary conditions on this general solution. And this is what we are going to do in the following examples. One example for Dirichlet and the other example for Neumann boundary conditions. Okay, let's solve an eigenfunction problem with all the details. Solve the following eigenfunction problem, which is the operator we are interested in proportional to the same function, so the second derivative of the function proportional to the same function, and now we have Dirichlet boundary conditions, homogeneous boundary condition, and L is different from 0, of course. So what is the solution here? Well, we have an equation of the form y double prime plus lambda y. Recall, we are looking for lambda and we are looking for y. So we are looking for lambda also. We don't know what lambda is. So we have this equation, and when we have an equation like that, what do? Second order constant coefficient equation. Well, we look for solutions y of x of the form exponential rx. As soon as we do that, we obtain the equation r squared plus lambda equals 0, which is the characteristic equation. And then we want to solve this equation. So this is the characteristic equation. This is something very well known from previous videos, but now the roots of this polynomial, so the solution of the characteristic equation, depend on the value of lambda, in particular whether lambda is positive, negative, or 0. So we have three cases here. The case A is when lambda is negative. The case B, we are going to call it when lambda is 0, and the case C, when lambda is positive. Okay, so let's start with case A. So lambda is negative. Because we assume lambda negative, we are going to write it as explicitly as negative something square. And the something, let's call it mu, is going to be positive. So then the negative sign is explicitly written. So now let's go back to the characteristic equation, and in the characteristic equation we have now we have r squared now minus mu squared is equal 0, or what is the same, r squared is equal mu squared, and then the roots are real, r plus minus, they're going to be plus or minus mu. These are the roots of this characteristic equation, so we have real roots. Okay, so now at this point we can use the boundary value problem theorem that we reviewed before, because the okay, let's write it down. The boundary value problem theorem, what does it say? The boundary value problem is going to say, because we have real roots of the characteristic polynomial, or just because the constant in the equation is negative, either case is fine, the boundary value problem has a unique solution. Unique solution for all boundary conditions, for all boundary conditions we are interested in. Okay, but we already know that the function y equals 0 is also a solution. Is a solution. You put 0 everywhere and it's going to solve the equations and the boundary conditions. So is a solution. Now the theorem says the solution is unique. So then y equals 0 is the only solution. But that concludes that there are no non-zero solutions, therefore there are no eigenfunctions. For recall, we are in the case lambda negative and Dirichlet boundary conditions. So in this case we don't have eigenfunctions, so we could move on to case B now. So here no eigenfunction, but before we move to case B, here we solve we conclude there are no eigenfunctions by invoking the theorem. Suppose you haven't seen the proof and you don't know how the theorem works, so can we continue the calculation not using the theorem and arrive at the same conclusion that there are no eigenfunctions? So this is what we are going to do now in the different color. So now we are going to check that actually there are no eigenfunctions, and we are not going to use the theorem. We are going to do the calculation. So what is the calculation we need to do? Well, we are right here, so we continue. That's all we need to do. So we continue. So we are going to check. We are going to go to a different color, and now we are checking. Check the result we found. Check. So how do we check the result? Well, we already know that r plus minus mu. So we know that mu is positive. What else we know? Well, then we know that the fundamental solutions of the equation plus minus are going to be exponential plus or minus mu x, isn't it? Then we get the general solution, and the general solution is going to be nothing more than a linear combination with c plus exponential mu x plus c minus exponential negative mu x. Okay, and now we have the Dirichlet boundary conditions. Which are 0 has to be the value of the function at 0 that we are looking for, and 0 has to be the value of the function at another point L. Alright, let's write down the first boundary condition. 0 is the value of the function at 0, but we have the general solution, so what is that going to be equal? It's going to be equal c plus plus c minus. Okay, the other boundary condition is the function at L. Alright, we evaluate the exponentials and we get mu L times c plus plus exponential negative mu L c minus. So now we need to solve this equation for c plus and c minus. Well, but we are going to use a little bit of linear algebra to solve it. So what do? Well, we can write it in matrix form as follows: 1, 1, exponential mu L, exponential negative mu L. Here we have a matrix of coefficient acting on the constants c plus and c minus, and all that has to be equal 0, 0. So how we can solve this problem? One way to solve this problem is to study this coefficient matrix A, in particular see if it's invertible or not. To see if it's invertible or not, we compute the determinant, which is going to be exponential negative mu L minus exponential positive mu L, or what is the same, 1 over exponential mu L minus exponential mu L. But this is always different from 0 when mu is positive. Actually different from 0, but we know that mu is positive, so this is always different from 0. So the matrix is actually invertible. So A is always invertible. And then what we have? Well, that implies we can solve for C, and then C plus and C minus. They're going to be equal the inverse matrix. We don't need to compute it because this matrix is multiplied by 0, so the result is 0. And this is the only solution. So from here we get that the only solution for the constants is 0 and 0. And therefore the only solution for the differential equation is 0, and there are no eigenfunctions. And that's it. So we conclude the same thing that we conclude with the theorem, and this shouldn't be a surprise because the proof of the theorem is actually this calculation in a more general way. But so we avoid doing this calculation. If we know the theorem, we can conclude no eigenfunctions in this case, lambda negative. What happens with lambda equals 0? So let's do that case now. Okay, lambda equals 0. That case is not in the theorem, so we need to actually do the calculation. So case B, lambda equals 0. Recall our boundary value problem theorem does not contain this case, so we cannot use the boundary value problem theorem for this case. So we need to do the calculation actually, but the calculation is pretty simple, so let's do it. So we have the characteristic equation r squared plus lambda equals 0, but lambda is 0, so we have r squared is equal 0, which means that the roots plus and the root minus, they are equal to each other, so let's call it r0, and they are both actually 0. Recall that when we have a repeat root, the general solution to the problem is a constant exponential the root times x plus c2 x exponential the root x, but now the root is 0, so that means that our general solution to the differential equation is nothing more than c1 plus c2 times x, which is obvious now that we write it, that this is going to be the solution, because the equation, after all, for lambda equals 0 is this. So what is the solution of the second order second derivative equals 0? A linear function in x. So everything looks okay so far. So now let's put the Dirichlet boundary conditions, and let's see what we get. Dirichlet boundary conditions. Well, what are these conditions? 0 has to be equal the function at 0, and 0 has to be the function at L. Okay, the first condition says that 0 is the function at 0, and that means c1 plus c2 times 0. So from here we get that c1 is 0. Okay, what do we get from the other condition? 0 is equal the function at L. Well, this is c1 plus c2 times L, but we already know that c1 is 0, so from here we get that c2L is 0, but L is different from 0. Actually, L is positive, so obviously from here we get that c2 is 0. And now c1 is 0, c2 is 0, so the only solution is y of x is equal 0. So this is the only solution to the problem, therefore no eigenfunctions. Alright, so case B, nothing. So I'm using red, so let's put that in red so looks better. There, no eigenfunction. So now the last case, case C. Case C, lambda is positive. Okay, for lambda positive, let's write that as lambda equal mu square, where mu is also positive. It's just to have a square there emphasizing that lambda is positive. So when we go to the characteristic equation, r squared plus mu squared equals 0, that means that r squared is actually negative mu squared, and from here we get that the roots are plus minus, they are going to be plus minus mu I. They are going to be complex. And because of that, the general solution of the problem, the general solution is going to be, for this case, case C, lambda positive, is going to be y of x is going to be some constant cosine of mu x plus some other constant sine of mu x. Alright, this is the general solution, and now we need to impose the Dirichlet one more time. Dirichlet boundary condition, which by now we know very well what they are. The function at 0 is equal 0, and 0 is equal the function at L. The first condition, 0 equal the function at 0, is C1 times 1, cosine of 0 is 1, plus C2 times 0, sine of 0 is 0. So from here we get that C1 is equal 0. At this point we are going to put this condition into the solution, and then we have that so far with one condition imposed, this term is not here, so we have only C2 sine of mu x. Okay, so we started with this general solution, then we add one boundary condition, and we ended up with this solution now. And now we still have one more condition to impose. The other condition is that 0 is equal the function at L, which is going to be C2 sine of mu L. Now if we choose C2 equals 0, which is one solution, C2 equals 0, then we recover the solution y of x 0, which we knew it was there, and here it is. But we can choose now C2 different from 0. And in this case, the condition for the boundary condition is sine of mu L has to be 0. But this equation has non-zero solutions. And actually, recall, this is an equation for lambda, because what was mu? Mu was nothing more than the square root of lambda L equals 0. So this is an equation for lambda. This is how we find the eigenvalues for lambda. We don't need the exclamation point. So how do we solve this? Well, the sine function has infinity many zeros. Sine of square root of lambda L equals 0 implies that square root of lambda times L is a multiple n pi. It's a multiple of pi, so there are many values of solutions, so we add a subindex here, lambda n, and here n could be 0, could be plus or minus 1, could be plus or minus 2, etc. But actually, lambda cannot be 0. Lambda n cannot be 0, because if n is 0, then for n equals 0, we get lambda equals 0, but this case we already studied before. This is the case we studied here. So lambda cannot be 0, so n cannot be 0, but it can be plus or minus 1, plus or minus 2, and so on. And then we have our solutions, which are lambda n, the eigenvalues are n pi over L square, and for each eigenvalue we have an eigenfunction, which is yn of x, which are here. Here. So we have a constant, C2, but now there are many C2s depending on which n we are choosing, and then sine of n pi x over L, and recall n can be all these values, but actually we could leave it here, but actually we are we are giving too many solutions because half of these solutions are not there. So what do I mean? Notice the following. Notice. Compute y of negative n. Suppose n is 2. What is y of negative 2? So when the index n is negative 2 of x. Well, this is some constant here for that index, whatever we choose, sine of negative n pi x over L. But whenever you have a negative inside the sign, this is the same as negative outside, then see the same constant we had before, sine of the positive n pi x over L. But this here is the other eigenfunction, isn't it? So here we have negative, we have c to negative n, and now if we divide by the constant we have chosen for n, then here we are going to get yn of x. So you see the eigenfunction with the negative index is actually proportional to the eigenfunction with the positive index. So these two are proportional, so they are not different eigenfunctions, for it's just they are proportional. So let's write that down. Y, where do we write it? Is maybe here. Y negative n of x is proportional to yn. So we don't need the negatives because they don't give us new eigenfunctions. They are always proportional to the positive ones. So the conclusion is that the eigenfunctions are, the eigenvalues are lambda n equal n pi over L square. The eigenfunctions n of x are this constant, let's call it Cn, sine of n pi x over L, but n only takes value 1, 2, 3, so on. The negative ones, they are not new eigenfunctions, they are included in these ones here. And this is how we solve the eigenfunction problem for the Dirichlet boundary conditions of our operator up there. Our second and last example today is to solve the eigenfunction problem for the same operator as before, but now with Neumann boundary condition that have has derivatives in both boundary conditions. So let's see if we can do it a little bit faster than before. So what is the equation we need to solve? The equation is y double prime plus lambda y equals 0 with Neumann boundary conditions, Neumann, which are the conditions we have there. Y at the derivative at 0 is equal 0, and the derivative at L of the function is equal 0. So what do? We solve the characteristic equation for our operator, lambda equals 0, and again we are going to have 4 cases. We're going to have the case A, which is going to be lambda negative, the case B when lambda is 0, and the case C when lambda is positive. Okay, let's start with case A. Lambda negative, we are doing the calculation a little bit faster because, well, we know more or less how this works. So lambda negative, okay, we are going to write lambda as negative mu square with mu positive. So we see the negative sign explicitly. And then we have r square minus mu square equals 0, just like before. And just like before, we get that r square is equal mu square, therefore the roots are just real numbers plus minus mu. And then from here we get the general solution. Let's put it here, the general solution of the differential equation, the same as before, which is y of x is going to be some constant, let's say c plus exponential mu x plus some constant c minus exponential minus mu x. Okay, so now all this is the same as in the previous example, but now the boundary conditions contains derivatives. So here is where the calculation is different, because we need to compute the derivative of the function to impose the boundary conditions. And the derivative is mu c plus exponential mu x minus mu c minus exponential minus mu x. And now the Neumann boundary condition. So Neumann boundary conditions, which recall 0 has to be the derivative at 0 and 0 has to be the derivative at L. So the first equation is nothing more than 0 is equal to the derivative. So mu c plus at 0, the exponential disappears, minus mu c minus exponential disappears. The other condition is the derivative at L. So we have mu, we have the exponential mu L c plus minus mu c minus exponential minus. Well, let's put the exponentials in the same place in both terms, minus mu L c minus. Well, this is a linear system of equations for the constant c plus and c minus, which has the following coefficient matrix: 1, not 1, mu, negative mu, and down here we have mu exponential mu L, and here we have minus mu exponential negative mu L. These coefficients multiplying the constant c plus and c minus, all that has to be equal 0, 0. This is what we need to solve. So we are going to be able to solve it if this matrix is invertible. So let's call it matrix A. Let's compute the determinant. And the determinant is going to be negative mu squared exponential negative mu L, minus minus is plus, this is an L here, mu squared. So what I'm doing is these two terms minus these two, mu squared exponential mu L. Okay, but this is nothing more than mu squared, and then what do we have? We have a negative 1 over exponential mu L minus plus exponential mu L. But this is different from 0. Recall, mu is different from 0. Actually, it's positive. So then this is different from 0. And then the system, then matrix A is invertible, and then C plus and C minus can be written as A inverse times 0, which is 0. So that implies that both the C plus is 0 and C minus is 0. And therefore the solution, y of x, there is only one solution, that is 0, and in this case we have no eigenfunctions. Alright, so this is the case lambda negative, Neumann. Boundary conditions. Okay, so but we have two more cases to go. So let's go to case B, which is lambda equals 0. Well, in lambda equals 0, this is easy. We need to solve the characteristic equation, recall, for lambda equals 0, which is going to be r squared equals 0, which means that we have a repeat root r equals 0. So we have our general solution. We computed already in the previous example, general solution, which is y of x is a constant plus another constant x. Recall now in this problem we need to compute derivatives of the solution because we have Neumann boundary conditions, and here the derivative is C2. So now the Neumann boundary conditions, recall, involve the derivative, and the derivatives are 0 has to be the derivative of the solution at 0, and 0 has to be the derivative of the solution at L. But in both cases we get the equation 0 is equal to, well, the function at 0, which is C2, and 0 has to be equal the derivative at L, which again is C2 because the derivative doesn't depend on x. So of course that means that C2 is 0. But what happened with C1? Well, it's completely free. Alright, so we got one eigenfunction then. Lambda, for lambda 0 equals 0, we get that y0 of x is any constant. Let's call it C0 now. So when C0 is different from 0, we have eigenfunctions. So let's put it here, different from 0, of course. Alright, we got a constant eigenfunction for the eigenvalue 0. Now, what happens if we are in the case lambda, case C, lambda positive? Okay, lambda positive now. Last case. Well, lambda positive means we can write lambda as mu squared with mu positive, and then we have our characteristic equation, which is r squared plus mu squared equals 0, and we have done this calculation before, so we don't need too much details to say that r plus minus is going to be plus minus mu I complex. And in this case we are going to get the general solutions given by y of x. It's going to be a constant, just like in the previous example, cosine of mu x plus another constant sine of mu x. Okay, but now we need a derivative because we are using Neumann boundary conditions that contain the derivative, and the derivative here is minus mu c1 sine of mu x, and here is mu c2 cosine of mu x. Okay, so now we can put the Neumann boundary conditions. And what are these boundary conditions? Well, as usual, 0 is the value of the function at 0, and 0 has to be the value, derivative, Neumann, and derivative at L. Okay, first condition is going to be 0 is equal the derivative at 0. So we have minus mu c1 and then multiply by 0 plus mu c2 multiplied by 1. Mu is different from 0, so recall this is different from 0, so that means that c2 is 0. So now is a good time to put this condition into the original function. So what we have here is that y of x, right now c2 has to be 0, so that is not there, and this is the function we are working with after one boundary condition, c1 cosine of mu x. Good, which means that its derivative is just negative mu c1 sine of mu x. Alright, now that we have that, we can impose the second boundary condition, and the second Neumann boundary condition is 0 is equal to what? To the derivative at L, and that is negative mu c1 sine of mu L. Alright, so here what we can do, recall, in this calculation, mu is different from 0. It's actually positive, but it's not 0. So that means two things. either C1 is 0, and then we recover, because C2 is 0, we recover the solution x equals 0, which we are not interested in, or C1 is different from 0, and that implies that the sign of mu L has to be 0. And we know already from the previous problem that this implies that this is a condition on mu, and therefore on lambda, because this is the same as saying the sign of the square root of lambda L is 0. Again, this is an equation for lambda, and the solutions are that lambda n square root times L is actually n pi, and recall that n could be 0, but now it's not, because we already covered that solution, and plus minus 1, but then at the end we are going to end up that n is equal to 1, 2, 3, infinity. The negatives are going to be eigenfunctions proportional to those, so just like we did before. So here we have lambda n is the same as before at the previous problem. But now the eigenfunctions yn of x, recall the sign comes from the derivative, but the functions that we are solving is the yn, so they are c1 n cosine of n pi x over L. And recall n is what we mentioned, 1 to infinity. So that's it. That is we've obtained eigenfunction, but now they are cosines for the Neumann problem. The eigenvalues are the same, the eigenfunctions are different. So in summary, because we may be forgetting something, summary, for Neumann boundary conditions, what do we get? Let's put it in red so we don't forget. We have an eigenvalue that is 0, and the corresponding eigenfunction y0 is any constant, any non-zero constant. And then we have eigenvalues n that they are positive, n pi over L squared, and the corresponding eigenfunctions are yn of x, that they are proportional, Cn, proportional to the cosine of n pi x over L, and here n is 1, 2, 3, infinity. And that is the solution of the problem for eigenfunction problem for the operator we are interested in for Neumann boundary conditions. We finished this video with a summary of the two calculations we have done. Here are the eigenfunction problem for the operator we are interested in with Dirichlet and Neumann boundary conditions. Here are the results, so we can compare. And then I add here also the results for mix 1 and mix 2 boundary conditions for the same problem. So we end up this video showing this result, and then you can actually go and complete the calculation for these two problems. This is a good place to stop. See you guys in the next video.